To underscore the usefulness of what we've learned so far, I wanted to take a quick look at how all this stuff comes together in some of the cutting edge biomechanics research software. Now, I don't know how clearly you can see this left-hand side of my screen over here, but if you look closely, you would see many very familiar parameters like maximum isometric force, optimal fiber length, tendon slack length, pennation angle, maximum contraction velocity. And this is just for one muscle. I have the left vastus lateralis muscle selected. This one, that red curve right there, is an implementation on a computer of this model right here, just this parallelogram with these different properties and a tendon and a pennation angle. And all of that comes together quite nicely. And of course, with the power of modern computing, you can just stack all of these together and have a model of all of the major, in this case, all the major muscles of the lower body. So you can start to understand how each of these muscles and how their specific properties contribute to something like walking or running, and even start asking questions about how much muscle force is necessary to run at a certain speed. The muscles are lighting up from blue to red right now, proportional to their activation, which is something we'll talk about next week. But that just goes from 0 to 1, 0 to 100% activation. But the forces that the muscles are producing when they're activated are dictated entirely by the things we've been learning about this week. The length of the muscle, the velocity of the muscle, the slack length of the tendon, the optimal fiber length, the physiological cross-sectional area. All of that comes together to enable simulations like this. So even though we've covered a good bit of fairly heavy and difficult material this week, hopefully you can see that it comes together in a very cool way to help us understand sports and rehabilitation movements that we might care about.